Guys, are we live now in YouTube? Is my audio hearing that particular stream? Hello, guys. Am I audible clear? So, we respect your dedication for coming to the day 3 of this workshop. Yeah, Hemavashini. Hemavashini, do you have any doubts to start with?
Yeah, that call is not working for me.
Yeah, we'll sort that out in the later part of this class. For
Um,
sure. Okay. For any kind of queries, you can ask. Like for this session, you can interrupt me anywhere and can ask any kind of questions. Or if any questions during the past sessions, you can ask after or during the later part of this session. So we are going to have a kind of surprise today, not like the Dragon movie, but a kind of surprise we can say, like an application part. So first of all, I have to say thank you to all of them here in this meet, spending their own time. And I'm promising that I'm not going to waste your time today. So let's move into what we are going to see today. Okay, let me present my screen. Yeah, yeah. I guess my screen is visible for no. Is it? Okay, okay, nice. So today, this is, as you know, our CoppeliaSim workshop, which is going good. So today we are going to see about the integration of sensors in CoppeliaSim. That's like there are three major types of sensors, which you are going to see in further parts. And the second part is surprise. I'll tell that. So we'll move to the first part, which is the sensor integration in CoppeliaSim. So basically in CoppeliaSim, we have major three kind of sensors, which include proximity, vision, and force sensors. I think you all know about what a sensor is. So it's a thing which is going to sense the physical things outside to the environment. The main thing is to get the physical things from the environment and to change it into electrical signal or whatever it want to do, and again it have to say the output in our presence. But in this CoppeliaSim software we are going to have some kind of ray based proximity sensors and camera based vision sensors and a force sensor. So we can't say what kind of theory it is going to be based on or what kind of concept the sensor is going to be based on, but we can say that a proximity sensor, it is like a model of the proximity sensor. So we'll dive into that first. So what is a proximity sensor actually? It is going to detect for a presence or absence of an object, whether it is there or not, it is going to say. So you can put it in a terms like it is going to give 0 if there is no object or 1 if there is object when I am speaking in terms of a digital sensor. So if you are not clear about what a digital and analog sensor is, you can always go to our last year summer workshop day 2, where we have clearly explained about what a sensor and what kind of major sensors we are using. And also in day 0, Nishwant explained about some various kind of sensors, I guess. In robotics, it is mainly used for things like obstacle detection, which we will be seeing then, and then grasping and navigation mainly. A main thing for a robot is localization and mapping. So for that, this kind of navigation, this proximity sensors will be helpful. And then obviously distance measurement using ultrasonic sensor will all do, and safety systems not to hit anything or some like. When we go to add, we'll see a proximity sensor here, and there are 6 type of proximity sensors we can see. I'll make that. So these proximity sensors that are here, and the cone type is more like the randomized ray type, so we can see that in like in align with each other. So this is a ray type proximity sensor where a single ray is going to detect whether an object is present or not. And you can see in a randomized ray, there are a random rays spread all over a particular angle of degree. And I'll say how to optimize each and everything in that. And in pyramid type, you can see an inner square and a far square, which are used to have a wide kind of range. And then a disk type, it is self-explanatory to see the vision as it is looking like a disk. And the cone type. You can see this. So I'll go to CoppeliaSim and I'll show the working of these proximity sensors, and I'll come back to the vision sensor afterwards. Okay, where's my CoppeliaSim? Yeah, it is here. So I have placed these 5 proximity sensors here with an obstacle here. I'll make it clear. Okay. So if you see, I have a ray type and a pyramid type, a disk type, cone type, and a cylinder type of proximity sensors here. And I have obstacles here. In order for a proximity sensor to detect, we have to make that obstacle first to be detectable. So for that, I have to make this cuboid. Let's say it's cuboid 4. I want cuboid 0. This is cuboid 0. So what I'm going to do is I'm going to the scene object properties and then to the object. Here you can see there are object special properties provided here. They're collidable, detectable, and measurable. These are the things mentioned here. So we want detectable. If you are working with a car or kind of thing, you can check this collidable box. And measurable means if you are going to use a proximity sensor for distance kind of measurement, or you are going to use some dummy objects which will be used for object distance measurements. So where we will check this distance box, sorry, measurements box. So in a similar way, I have did for all. You can see the objects here. I have checked the collidable and detectable for everything. And you can see I have all these proximity sensors. This one aligned here, but all these are not the same. So instead of doing rotating each and everything singly, we'll take more time. For that, I'm going to show you a small trick. So if you want a thing to be rotated by the same, okay, I will say this is in this orientation, but this pyramid is in this orientation. So I have to make this orientation to this kind. If I want this, what is this sensor actually? If I see, this is proximity sensor 3 and this is proximity sensor 2. If I want this proximity sensor 3 to be oriented in the same way of 2, I'll press shift and select this. So you can see this is the main sensor and this is the selection. If I want the same orientation, I'll go here and you can see apply to selection box here. So if you give apply to selection here, you can see the orientation shifted alongside this. I explained this using disk because if I use cone or anything else, you can't visualize that properly. So that's why. So I want these all proximity sensors to be in the same orientation of this. So that's why what I'm doing is I'm going to select all these 4 and this proximity sensor 0. You can see these are all in yellow and this in white because this is the selection what we are going to use. And if I give apply to selection, you can see. Now, this proximity sensor, if you click, which is the ray type proximity sensor, if you click, the scene object properties will be seen. Inside volume parameters, we can see the various proximity sensor characteristics. For a ray type, we can only have the range. So if it is 0.4, this is up to this. If I reduce this to 0.2, you can see the size of this particular, which is the range of this particular ray type proximity sensor decreases. So I'll place this back to 0.4. For what is this? Cylindrical type proximity sensor, we're having the same, but in additional to that, we have an angle. If I extend this angle to 120 degree, you can see this difference. The way in which we are setting the angle, it will make the accurate or wide range of vision. So this is how we are going to plan for. And this is what we call a pyramid type proximity sensor. If we go to this, we'll have X size M in meters, Y size in meter, and X size for and Y size for. So if this is X and Y for this particular inner box, which is the inner pyramidal box, I think you can visualize. So if I change the what we say, if I change the size of this, you can see it changed into a square, or if I want to change whatever, I can do that. And similarly for the outer square, I can change this as I wish. So you can see, but this sensor is not up to the mark of that particular obstacle. So what I want to increase the range. So I'll increase the range to 0.4. You can see the proximity sensor can see that. I'll show how it can see that actually. And then what is this proximity sensor 3? I'll go to the volume parameters. You can see there is y size and inside gap along with the angle. So if I increase the angle, let's say by 120 degree, you can see the radius of the curvature of that particular arc of sector is increasing. And you can have kind of multiple phases. If I have phase count of 42 inside, you can see here the density of the lines that are going to make the phase will increase. And in a similar way, this is the radius of the curvature, which is the arc of sector for that particular circle is. And this y size is what we are saying, like the width of this particular thing will increase. So I'll make this. If the same kind, I want to increase the range so that I can detect this. In a similar way to the cylindrical proximity sensor, it also act in the same way. But the thing is that we can have this range and angle. In addition to that, we have inner face and outer face similar to disk type. So we can say that a cone type proximity sensor is an addition of both disk type and cylindrical type proximity sensors. So as you can see, I have made it all up to the range. And the thing is, the obstacles are made detectable. But when we are going for an application purpose, the floor will be always detectable. But I don't want that floor to be detectable. Rather, it should not be detected by the proximity sensors or whatever I use. So I'll go to the scene object property of the
Karthikeyan,
floor.
sorry to interrupt. Actually,
Yeah,
Prishidasri have asked
that's fine.
what is the phase count for?
Okay. Thank you. The phase count is nothing but it is like the resolution between, if I can say, like between these two slits, that if any object is there or less than the thickness of that particular slit, if an object is there, it will not detect. As I increase the phase count, the slits will be in a very minor way. What can I say? The thickness will be lesser so that it can detect even a very minute particle that is in the way of that particular bot. When we are going for a maximized or we want no obstacle to be detected, that kind of maximity, we'll use an increased phase count in both inside and far regions. I guess, Prashidastri?
Yeah, I got it. Thank you so much.
Yeah. And now, but the floor should not be detected. So that's why what I'm going to do is I'm going to the scene object properties of that floor, and here I'll check this object is model, and I'm going to the model properties where I'm going to make this floor as not detectable, which makes this by any chance, maybe by default the floor can be detectable or not detectable, but I'm making sure that the floor is not detectable. So if I run the simulation, you can see the yellow lines, which makes sure that the sensor is sensing a particular obstacle here. So I can say, if this sensor is moving, the yellow lines will be oriented towards the obstacle. I'll show that in our later part. And you can see this is how they'll detect. If I make this cube, let's say cuboid 4 as not detectable weight, as not detectable, you can see the yellow line isn't appearing, which means this ray type sensor is not seeing any kind of vision now. So I guess you can visualize this. I guess you all got the point. If yes, give any emojis if possible. Yeah, nice, awesome. Let's go to the next part. The next part we are going to focus on is a vision sensor. What actually is a vision sensor? We all usually do image processing, video processing, and a lot of things. And in this kind of modern world, we are going for a much CV based, computer vision based things. For that kind of properties, we need a vision sensor. Vision sensor is basically just a camera. We can modify their resolution and everything. So this kind of vision sensors are used majorly in object recognition. There are many projects out there in LinkedIn, GitHub, where they are using object recognition, like this is a chair, this is a bed, and kind of things. And color detection, an important thing. We are going to do that kind of thing using our later sessions. And navigation and SLAM. SLAM is what I said, the localization and mapping. And this Aruko detection. Aruko detection is a kind of QR code, or what we actually use QR code, right? In a similar way, Aruko IDs are available. They have their own decoder values. So these kind of things are used for vision sensors. We are not going for image processing or computer vision. If you want a detailed vision of that, we'll provide that particular PPT where we had an offline workshop for the previous year. So if possible, I'll check it out and send you the previous PPT for image processing. So if you go to add vision sensor, you can see two types of vision sensors out there, which is one is a perspective type and another one is the orthogonal type. This perspective type is, you can see a perspective image, like some kind of perspective drawings where they draw an entire building in a same view. Or to be clear, I can say that in camera there is a setting called panorama moving light, right? Where we can start the camera and we can move in a particular way. After that, it will be recognized as a photo, which is actually a perspective photo. So for that kind of things, we use perspective type camera, and an orthogonal type is a straight vision camera. So these two are what we are going to see. I am having a demo at the later part, but I am going to just say how it is going to see. So in order, I have already placed a perspective and an orthogonal type vision sensor here itself. And I said, no, we have to make these things visible. So the same thing, it should be visible. If you don't want, I'll say, if you don't want the floor to be visible, as I said earlier, and go to object model properties and make sure it is not visible. If you see means, while detecting by the camera, the floor will be not visible. But I don't want the floor to be not visible, so I'll uncheck that. So now we are going to see the output of the vision sensor, but how? This is just a box light. So how can we see that? So for that, right click in the environment and select add floating view. If you see in the floating view, there is nothing. You can have, see, if you go into this page selector, you have multiple kind of visions for the environment. If you go to the top view, there is a floating window for this XYZ camera proxy. This is a floating window for that particular dummy. So for vision sensor to be displayed in the floating window, what I have to do is I have to select that vision sensor and I go into right click on the floating view, and then associate view the selected vision sensor. If I place like that, you can see the vision sensor 0, which is the perspective type, is seen here, and these sensors are not visible and their ray is also not visible. If I see the view of this particular vision sensor 1, which is the orthogonal type, I want to add another floating window and I am going to view it with the vision sensor 1. You can see this is a gray kind of thing, and as you can see, this narrow path is directed towards this particular cuboid. So if I want to make it above, I think it will not update. This is an updated view because I simulated dumbly once. If I again simulate only, the current view will be updated. You can see this is the environment, which is the black environment, and this is the cube. So that's all for the sensor integration part. So if we go for the next, which is the force sensor is actually what I can say, it is a very kind of big concept, because we are going to use it in multiple various kind of manipulators, where we are going to know whether the end effector is going to have some kind of object. We have to know what force it is carrying and whether the force is in the range of what the manipulator is designed for. or in other things, if you want to move the manipulator in different kind of orientation, we have to know whether the torque. So we have various links in a manipulator, right? So each link will have a particular torque oriented with it. So whether we have to know whether everything is in set property. So for that we are going to have a force sensor, which is like a dummy cylinder with a rod inserted. But the thing is, it will give the torque in all direction and force in all directions. I don't have a current working model for the force sensor, but I do have a very dummy kind of scene. Yeah, this, I have one cuboid and another cuboid on that. So in between, I have placed the force sensor and I modeled it to print the value of that particular block in it. If you see, the force is acting only on the z-axis. So you can see the force is only acting on the z-axis and there is no torque available. That's why it is only printing 9.81, which is actually the weight in Newton for that particular cuboid. So actually, they'll use force sensors majorly for calculating force and torque transmitted between two particular objects. That's why I placed a below cuboid and an above cuboid. So this force sensor is used in robotics, as I said, for grasping control and force feedbacks, what we use in manipulators, and between human robot interaction, because there are digital twins that will replicate the original manipulators as a 3D model. So in that kind of things, when humans enter, it should follow the laws of robotics, obviously, right? So it should know whether an object is moving in the conveyor belt or a human is moving in a conveyor belt. So this can be made by knowing the force sensor, force value of that particular vision. So I guess we are all having a good day until now. Yeah, guys, you can put any emojis for ah nice Danisha, Rohit, Hariharan. Yeah, good. We're having a good session over here. Is there any doubts until now what we are seeing for sensor integration? So now I guess PDF would be shared within the group. Varshini, I think you can share it now. So the session isn't over. Actually, to say, the session has started by now. So today we are going to see something very realistic, like not realistic in the sense, not in a real way, but we are going to do some actual bots in CoppeliaSim in a simulated manner. So you can see something here. What is this doing? What is this doing? What is this actually? So we are going to have some kind of robots. We are going to work with some kind of robots which are actually obstacle avoidance robot, a wall following robot, which is actually a right following because I have inserted a sensor in the right. And we are going to know about one new algorithm which is called a Buck2 algorithm. And along with it, as I said earlier, I have a demo for the vision sensor. So I guess we dive on to that. How many of you are interested, or how aggressive you are to learn this obstacle avoidance robot? Yeah, nice. With this energy, we can go to the first bot, which is the obstacle avoidance bot. So what actually an obstacle avoidance bot should do? Can any of you open your mic and say what their logic could be? I want responses, if possible, from you guys. Even in the
If there
chat
is
box,
any
I can.
if there is any obstacle, it should either pause or it should change the direction.
Yeah, exactly. So what we are going to do in here is we are going to have one proximity sensor in the front and we are going to detect the front obstacle. If an obstacle is detected, we are going to tilt the particular bot in a degree until where the object isn't detected. So this is obstacle avoidance is a basic thing for every kind of bot you move. For any bot, the environment detection is an important thing, and for that you need a proximity sensor, and the concept behind it would be obstacle avoidance. So I want to go to the, what I say, obstacle avoidance bot code. After I explain this, I'll simulate it and show you. So I am going to have a left joint and right joint, which is a two-wheel bot I'm having today. So if you have four-wheel bot, no problem at all. You can, whatever I am doing for one wheel in the left and one wheel in the right, you can do it for the two wheels in the left and two wheels in the right. So I'm defining a state called forward, and I'm going to make this avoid duration by 0.6. You can change this avoid duration. This avoid duration is nothing but how much time you are going to recheck for whether the obstacle is present or not. And this is the forward speed in which the robot base is going to move. So I'm getting the object for both the left joint, right joint, and the front sensor. We can directly use slash left joint, slash right joint, or slash front sensor. But I usually prefer this kind of way of getting the object because I always like hierarchies to be going. So the main base of that body I have defined it as a robot base, and I'll show you that. And then from that robot base, I am calling this left joint. So these three I'm going to place it in left joint, right joint, and the front sensor. And I'm going to make sure that all of these are present in the whatever I have placed. So I'm going, if the left joint or right joint gives a default value of -1, which means they are not there, the thing is the object handle error, there is no. And here I have used add status bar message, which is nothing but a print kind of statement, but this is going to have the higher kind of priorities than print. So I'll use this status bar message, which is going to be printed in that particular status bar as a message, not as a statement. So if not, if the left joint, right joint, and the front sensor, all the things are recognized, I'm going to have the robot as initialized. So this is what we do in initialization, and we are going to the actuation. So actually, if you have worked with the Arduino or kind of things, you would see two functions like void setup and void loop. The void setup is going to be similar to what initialization is, and the void loop is nothing but this activation. So it is going to run for multiple times until the simulation is going. So I have a new kind of function, which is read proximity sensor. This is the function we all use for any kind of proximity sensor we use, and this is going to return two values to us. One is the result, either 0 or 1, which is detected or not, and the distance of where the obstacle is present. So for that, you have to enable the measurable option in your obstacle. And I am reading the front sensor. I'm storing it in result and distance. I'm getting the time of that particular instant where the obstacle is detected. So if not, whatever, I am getting the current simulation time in a variable called time now, because I'm going to use that time now variable. So if the state is forward, because defaultly the robot is going to move forward, if the state is forward, and if the result is greater than 0, which means either 0 or 1 means the obstacle is detected. So if the result is greater than 0, I am going to change the state from forward to avoid. In avoid state, what I am going to do, I'll say here. So just wait for that. So that avoid start time. So we have defined an avoid duration here, right? And avoid start time equal to 0 initially. So now I am going to make that avoid start time is equal to the simulation time at that particular instant. I am making this clear because when we are going for a higher coach, you will be not understanding this. That's why I'm implementing this very deeply. And I am making a message if the obstacle is turning right now. Else, if an obstacle is detected, then what we have to go? We have to make both the joints to move in the forward speed, which is the forward speed I have defined as the base speed, which is 10, and I'm making both the joints to move in 10. If the state is avoid, what we have to do? If the state is avoid, we have to make the left joint and right joint to move in any particular direction. If you want to move the bot in right side, you can change the signs of the left and right. I am making the bot to turn in left. That's why I am slowing down the uh, movement, which is the velocity of the joint in negative direction, and the velocity of the right joint in positive. And I have defined the turns you can as I all. So this thing is clear for now, I guess. if the time now minus avoid start time. This avoid start time is the time when the obstacle is detected, and the time now is the current simulation time. If the difference is greater than avoid duration, which is I defined it as zero point 0.6. If it, what I'm basically saying is, if we have crossed the obstacle, we can change the motion to forward again, which is both the joints should move in the forward direction. And I'm printing a status bar messages. I have avoided the obstacle and I'm moving again. And basically, I am cleaning it up just for the cleanup. So I'm making left and right joints to be zero. Wait, is there any doubts? No, right? So we'll move to the I'll open this. So I have already manipulated these three obstacles regarding to the movement of this particular bot. If you see, I have made this left joint and right joint as what is it? As velocity mode with a maximum target velocity of 5 newton per meter. Maximum torque of 5 newton per meter, and a target velocity for 90 degree per second. So I have defined it for both the joints, and you can see my bot is having a front sensor at its edge in the front. So I have implemented this script here and these three obstacles here. If I make this move, it will go slowly. The thing in each simulation is it will take time to simulate. That's why for from the next particular simulation, I'm going to start the simulation and I'll go explain the code, and I'll come back to the simulation whether to check the goal is reached or not. So you can see once again. You can see once the obstacle is detected, it is turning, and when it is greater than the avoid duration, I am making it move forward, and the same thing is going to happen. And I can change the range and other things of that sensor to make everything. So I guess you all clear with it. I'll make a small change here to make you understand. So I am changing this direction of motion, and if you can see, it is moving in the right direction. I guess you are all having fun with this. Did you understood, everyone? Just put a thumbs up over here. Yeah, Danisha. Super. We are having a great reaction over here. I guess all of one here have understood the obstacle avoidance logic. And here with I'm going for the right wall following bot. Prior to that, I'll open that wall following.ttt. Here I'll basically explain what we are going to do. Just for the sake, I have prepared a PPT. I'll make this. Yeah, what a good animation. Okay, now I have defined as the same bot, but two sensors here for now. So what I'm having is a front sensor and a right sensor, which is oriented in their respective directions, and I am having them both under my robot base. And as usual, I have my right joint and left joint with their wheels respectively, and I am having a dummy here. This dummy is nothing but this is going to just a nothing, but it is going to give some coordinates measurement for that. It is actually nothing but having a special meaning. We can't say dummy is actually wasted. So, and I'm having again a goal here, which is this particular point, and there is actually nothing there, but I am going to use this robot dummy and goal, which are the most important thing for this particular code. So you know the importance of this when I go for the explanation of that code. So let me go into that. This is the right wall following bot. So I'm having left joint, right joint. I'll have a speed run here, and the front sensor, right sensor. This is what we are going to use: robot dummy handle and goal dummy. So for a right wall following robot, can anyone say what's the logic behind it, or what will happen, what we have to achieve? Anyone? Just open your mic and say what we have to. Just the name itself, it is self-explanatory, right? Right wall following means any logic behind this, because if you are going to follow the wall on the right, you have to maintain some distance between the bot and the wall, the first thing. And the second thing is, if there is a sudden turn in the wall, as you can see in my environment, I have a sharp turn here. So in this kind of sharp turns, this front sensor is going to act an important thing. So once the front sensor is detected, I want to make a sharp turn or something like that. And the third thing is the emergency case. While I am keeping some duration initially, I can't say there isn't anything in my way. So I am making sure that if any object is going less than some defined distance, I have to make an emergency backward pull for that particular bot, and then I have to follow the wall again. So if these three things are only valid when the wall is present. If there is no wall, what I have to do? I have to search for the wall. So what I'm going to do is I'm going to make the bot to slowly turn towards the right side and search for the wall whether it is present or not. So these three cases are the main logic behind what we are going to do for a right wall following bot. So I have defined a forward speed which is 0.35, which is way bit slower, but how much slower the bot speed is, that much accurately you can have turning, or you can achieve that much percent of victory towards your goal. And slow and steady wins the race, right? So again, turn KPWF. Turn KP is nothing but we are going to turn wall follow. WF means actually wall follow. So we have to turn this turn speed. What we have defined in obstacle avoidance is nothing the same here. It's point. This is the wall. The distance between the wall and bot. I'm setting this as 0 in meters. So you can see whenever if you have doubt in the code, I have implemented some these kind of command lines here. And to an important thing, similar to what we have double slash in C or slash in C++, we have double hyphen in Lua for writing command lines. So after making sure this, and this is having emergency turn speed, emergency reverse speed. These two things are important when we are going for industrial kind of things. These are important backup. So we'll go into the code. I'm getting all the objects. As you can see, when you go for some complex structure, this kind of practice will be helpful for you. Defining the parent and their child will be to know the hierarchy, not to go to again to the simulation and I have to show you whether that is present or not, like that. So Android base, the left joint is there, right joint is there, front sensor, right sensor, and the robot dummy is there. And the goal defined in the main. So I'm giving particular handle respectively. If some1 is giving -1 value, I am going to give a verbosity script error. This is nothing but similar to what we have did in add status bar message. This is also going to print, but as an error. As an error means if we see this thing executing, the code will stop. So it is a script error. So we are having all the handle over the code. We can stop the simulation through the code using this particular verbosity script error. If you want a lot of functions where it is and how can I know all these functions, you go to yesterday's PDF what we have sent, and the bottom we have a reference manual. That manual is consisting all of the functions that is given for Lua or Python, both in defined by the Coppelia Robotics, their own website. So again, I'm similarly for all, if they return -1, it is meaning that there is nothing. So I'm not going much about here. And I'm having, this is if all handles are valid is true, I'm going to make sure whether it is true. If not all handles are valid, that is I'm going to stop the simulation. And else, if everything is good working properly, I'm going to make sure this right wall follower bot is initialized, and we are going to do this actuation part is what we are going to focus mainly on. I'm again making sure this, if anything here is -1, I'm going to make sure it is not, the bot is not moving, so I'm making all of us at 0. This also in other terms make initializes this left and right joint proximity. Now we are going to read both the proximity sensors and we are going to act depending upon that. If you see, I am having a friend detected and detected. This distance and all we are not going to use, but however, as it is going to return, if you don't give that, it may show an error. So each function is having its own function and we have to work depending upon that. So I am getting the sensor value from both the sensor and again I am going to get the object position. This is also defined in that particular what we link robotics. This object position will give you a small representation of that whatever say here is the objects, the robot dummy handle and the goal dummy handle. So this post robot and post goal is going to have the X, Y, and Z orientations of all these robot and goal. So if and the same way, same way is checked for left and right joints, I am going to make sure if both are none of either of them is not present, I am going to terminate the simulation, giving a runtime error. Now I'm going to calculate the x distance and y distance between the goal and the robot. So this is what I meant actually. So what we'll do for distance calculation between 2 points? It is easy, right? Can say, right? If you want to know the distance between 2 points that is in x and y plane, so what you will do for that,
y2 minus
guys?
root of y2 minus y1 the whole square and x2 minus x1 the whole square.
Yeah, nice. So this is what we are going to do. And as she said, we are going to the goal position minus robot position, which is 1. As Jaisnav has explained yesterday, there is no zero index table from 1 to 3, 4 like that. For dx, I am taking goal 1, robot 1, which is actually the x-axis, and similar way y2 minus y1. And y is square root of x square plus y square, which is the distance to goal. So from here, I have defined the distance between goal and the robot dummy. This is going to help in checking whether the goal is reached or not. When the distance to goal is less than 0.5, as it is going to calculate for every time instant, when it is going less than 0.01 0.15, yeah, my goal is reached, I have to say that, and I have to stop the simulation. So I am making this as both the joint velocities as 0, and I am going to make the goal reach stopping simulation, and we have an inbuilt function stop simulation which makes the simulation to stop. We can't use verbosity script error here because there is no error here. If you want to stop the simulation using verbosity script error, you can't use that. You're always welcome. But as we are having a direct stop simulation, we can use that. And this thing is the right wall following logic. So I have the left joint velocity in wall follow mode and right joint velocity in wall follow mode. So this thing is actually the forward speed when there is nothing detected. When I'm going for the right wall, I have to tune this accordingly. So rule 1, emergency is always the priority. So I am defining for that. When the front detected is greater than 0 and the distance is less than 0.2, here the distance comes to play a major role here. If it is less than 0.2, we have to make a sudden backward turn. So I am changing the left joint and right joint velocities as minus forward speed multiplied by their scaling, respective scaling. This scaling I have already set to note for you. Emergency reverse speed and emergency turn speed I have already defined. Uh, if you can see, emergency turn speed and emergency reverse speed, which is 2 and 0.5. We are going to have this as a factor. So if the robot's bot is actually moving in 0.35, we are going to multiply it by 0.5 to make it move back. And in a similar way, if it is 5 into 2, which is a ratio of 10, we are going to turn the bot in the backward direction. That's why I am using the negative sign in defining their velocities. Yeah, we are here. So I have defined both their velocities. Left wheel velocity is negative and right wheel velocity is positive, which means in what direction is it going to move? Left or right? If the left side is rolling in negative and right side is moving in a positive direction, which side the bot is going to turn? Just visualize and say. Bros, I'm audible, right? I think I'm audible. Just a basic question, whether if the left joint is moving in an opposite way and the right joint is moving in a forward way, the bot is going to turn in which direction?
Right side?
See, say once, wait. Yeah. If left joint is moving in a reverse way and right joint is moving in a forward way, the bot is going to turn like this in the left direction. So I guess you can right side, this is gonna turn like this, which is in the left side actually. Now can you understand, Prasidarshi?
Yes, got it.
Yeah. Now eyes what going to move in a left turn. So when there is a emergency point 2 is detected, and again I'm going to maintain, this is an emergency step, and this is the maintain the distance to wall on the right side. So if you maintain that particular distance there, what I have to make sure is the right side distance should not be less than a particular value and the value should be maintained between them. So I'm having a new variable called a distance error, which is actually the distance between the right distance, which is the sensor detected value, and the set point what I have defined. This set point I have defined, I guess, zero point 0.3 meters. So I have to make sure whether the distance is greater than that. If distance error is greater than particular value, I have to make that value to zero point 0.3. Let's say the distance error is 0.2, which is positive, which means I have to make the distance error 0 by turning right. If the distance error is negative, to turn left to make sure that uh, the distance is maintained. Like let's say the right distance is returning 0.1, then the distance will be minus 0.2. So in that case, I have to make the joint to left direction. So in other words, I can say if the distance error is positive, the left velocity should increase and right wheel velocity should decrease. You can see the distance error and the left wheel velocity both are having a directional proportionality. The right velocity is having a proportionality between them. So I am having the left wheel velocity once the distance error is positive. I am going to have a negative sign here, which makes and the directionally proportionality because when you have a negative sign in the second term, wheel velocity a higher value. For example, 5 minus 3 would be 2 and 5 minus 2 would be 3. So 3 is a greater value. So having sign here and the left should be in a proportionality and this right velocity in an inverse proportionality. That's why I'm making a plus here. So I guess you can understand. So now I'm going for the maximum velocity. The maximum velocity making the maximum wheel speed, which is 2 times the actual forward speed I have mentioned. When the left wheel or the right wheel velocity goes greater than the max wheel speed, I have to make that equal to the maximum speed. So that's why I'm using the minimum of these two. let's have a condition like the left wheel velocity is greater than the max wheel speed. So these two, when compared, will be having the minimum, which is the max wheel speed. And among this minus max wheel speed and plus max wheel speed, our maximum value would be plus max wheel speed, and the left joint is going to rotate in plus max wheel speed. Can you understand? Or did I make it complex? Guys?
Could you explain the last part again?
Yeah, I'll say that. If see, I have to make the bot to move in a particular maximum value, that is my maximum boundary. It's this. So I am doing minimum of the velocity and the wheel speed. Let's say, let's have two conditions. Clearly have that. I am having, which is the faster way than the maximum allowed speed. Then greater and maximum wheel speed will be smaller. I'm taking the minimum of these two, which will return the maximum wheel speed here. Instead of this particular space, I'll have maximum wheel speed. So among the negative maximum wheel speed and positive maximum wheel speed, which is the maximum? The positive maximum, obviously. So the instead of left wheel moving above the allowed speed, it is going to be shrink it down. Let's have the second condition. If the left wheel speed is more negative, which means the more backward high speed, I'll going to calculate the minimum of these two. Actually, the left wheel velocity would be minimum as it is going in a very faster backward motion, so having high negative value. So let's say max wheel speed is minus 10, and this value is minus 20. So now I am going to calculate the maximum of these two. Which is maximum, minus 10 or minus 20? Obviously minus 10. So now we are going to have the maximum value as the minus max wheel speed, which is the negative allowed maximum speed. I guess you can visualize it to some extent. Now, Rashida Sri. Yeah, good. I guess you have got this point. And now we are 95 percentage there to complete this right wall following robot. This is what the else condition, which is the if condition we had is the emergency situation, and the second condition would be the right detected is greater than 0, which is there is something detected. If there isn't any wall there, so what we are going to do, we have to slowly turn towards right side and search for a wall, which is I have some kind of scaling factor to make sure the bot is moving slowly towards the right side with a lesser angle of rotation. So I am decreasing the right right side by zero point 0.3 and left side by 1, so that I can have a higher speed in the left wheel and a lower speed in the right wheel, which makes the bot to slightly turn towards the right side with this same forward speed. So I guess you can understand, we are going to search for a wall. If wall found, we are going to maintain a distance, and if there is an emergency, we are going to take a sharp turn with already some scaling factors given. So we have calculated this LVWF, RVWF after all these particular thing we have did for if else conditions. It will have a final LVWF, which is in the range of minus max wheel speed to plus max wheel speed. So this velocity we are going to set for the respective joints. Again, we are going to add a status bar message to know that the distance to goal is this. When this goes less than 0.5, our simulation will be stopped. And if we have to, if we want to know whether the front is detected or not, we can print this, and we can have multiple kind of string formats here. I have printed this what distance to goal here, and I printed front distance here, right detected everything here. So I am cleaning up just that it is, we are having our right wall following bot algorithm finished. So we'll move to the simulation. This would be slower, I guess. So what I'll do is, just you can see it is having a slower right turn. Yes, the set point is reached, and then we are going to have the distance error to make it 0. I am making the distance error 0, and I am going to be in the forward direction. And here I want a sharp turn, and again I want to go in a similar fashion towards a goal. So this simulation will 0.35 forward speed, so it is gonna take some time. In the meanwhile, I am going to make sure that anyone is having any doubts here, guys. You all clear? I saw thumbs up exploding here. So yeah, we'll move to the next logic, which is the bug. Before going into the bug to algorithm, I want to make sure that what's a bug algorithm is. A bug algorithm is basically something which is going to be defined for from a start point to a goal point. There are multiple ways of achieving it, but what if obstacle is there between the start point and termination point? So what we are going to do for that? So there are three algorithms defined for that. One is a bug zero algorithm, another one is a bug one and bug two algorithms. For the bug zero algorithm, we are going to search for the vision of the goal. I am going from here towards the goal, which is the termination point. If I find I am going to follow the right wall, at this position I can see from this bot's orientation. If it can see the termination point, it will go. And again, if another in that particular orientation, if it sees the termination point, it will go like this. But there is a very important issue here. Can anyone say that what is the issue with the bug zero algorithm? Can you say what's so this vision is an important thing. If the bot goes in the particular obstacle and if it can't see the termination point, imagine if this circle is up to this, let's say, uh, I'll say like this circle is like this. I can't see from here, right? There is no vision from this particular point to the termination point. So what it will do, it will again loop, and it will go for infinite times. So that's why I'm saying bug zero algorithm has one of the major disadvantages. So that's why we are going to move for a bug one algorithm. Bug one algorithm is nothing but a calculation of the closest point. What it actually does is it is going to follow the same thing, and if obstacle detected is going to follow the right wall, and for each is going to calculate what's the distance from that particular location and that so for one complete rotation it will take the readings for everything, and if it sees at this point I have the closest distance, if it sees like that, again for the second rotation it is going to go, and when that point is reached it is going to go there. And when second obstacle is reached, it is going to do the same thing for one rotation, and from the closest point it will go to the termination point. But can you say what is the wrong thing or what is the disadvantage here? It's obvious, right? We have to go for one complete rotation to check whether the termination point is there or not. So this is going to take a lot of waste time to have one complete rotation over the obstacle. We have to make the bot follow for that. And the main thing you can see for this particular thing, which is a easier obstacle, right wall, it is taking this much time to rotate, having a good kind of precision. But if we go for a very larger or complex shapes, it is very complicated to have one full rotation and again to go to the closest point, right? So that's why bug one algorithm has this disadvantage, and we are going to reach the goal in our life. See, the distance to goal is decreasing 0.55, 54, 53, like that it is decreasing. And once it goes less than 0.15, we are going to have the simulation stopped with the goal reached successfully. Status bar message. So we are having a top view here. So to check whether the bot is reached here or not. So I am 99% there to reach the goal. So we'll have this symbol for the goal reached, guys. I'm going to see that from you. 0.9, 0.8, 0.7, 0.6, and 0.5. Yeah, yeah, finally. Hooray! Wow, what? We have we have reached the goal, which is once the distance to goal is less than 0.5. Yes, we got everything and we reached to our goal. So now, yeah, nice. So I'm going to the bug 2 algorithm. Bug 2 algorithm is a complex for computations, but it is the best possible way to reach the goal if whatever the obstacle is there. So what is the thing here is we are going to draw an imaginary displacement line between the start and termination points. So let's say this is the imaginary line. Whenever the obstacle is detected, it is going to follow the right wall. As I have said you the right wall implementation, I'm using right wall here. And once the I will say this imaginary line as m derived line actually. Once this m line is seen again, it will turn the orientation towards the termination and goes in this way. And again, if an obstacle is detected, it's going to follow this. And once the m line is seen, yeah, that's it. We are going to go back to the termination. But this is not at all as much simple as we say. So we have got a lot of logics to recheck whether the M line is reached or not. So this is a pretty big code, but I'm going to explain it in a simple way possible for me. So as always, we are having a left joint, right joint, robot dummy, and goal dummy. And the logic is going to vary. This is the base speed, that is the forward speed, and the turn KP always. So the wall follow speed, wall turn KP, wall distance set point, these are all we know actually. And then emergency turn speed, emergency reverse speed is everything all we know. So for bug 2, I am going to define 3 states. One is the move to goal, another one is the state wall follow, another one is to backup. So these 3 are the main states that we are going to use. So what is the logic for that? As I already said, we are going to initially change the orientation of the bot towards the goal, and we are going to go along the M line. And if obstacle is detected, we are going to start to from move to goal to wall follow condition. We'll go to follow the wall. If any closer or emergency condition is reached, we are going for a backing up condition and again wall follow. And if the M line is seen again, going back the orientation to terminate, we are moving towards the state move to goal condition. So this is pretty simpler, right? Yeah, it is. So I'm defining a hit point and initial distance to goal at hit. Hit point is nothing but where the robot sees the obstacle in its M line. So I think I can show that. Wait, recent scene. I have bug 2 here. So my goal is here and my robot dummy is here. So this would be the M line. So it is going first, it will change the orientation towards this and it will go. The instance it will see this obstacle, right? That is the hit point. So we are going to have that hit point position here, and then we are going to have a recheck for every 0.5 seconds that I have given as a recheck interval, and a backup duration and backup start time. This is for backing up when there is emergency conditions reached. So initializations, as always, what we have did in the last part. So we are going to do the same again. So I guess you can skip this, you know all this. And the same thing, I am going to get the value for the sensors and pre-check something. I'll do this and all very simple. If it returns -1, we are going to make sure that it is not. And here I'm reading the proximity sensor values with the front detector, right detector, and then raw distance from them. So if the front distance is equal to both when distance raw, see this thing is what we are going to say. If there is any obstacle is there, I am going to make the front distance value to be distance raw, or else I am going to have some dummy values. I am having a dummy, but it should be larger to make sure that the distance is high. Front distance is high means there is an obstacle 999 meters from now. It is actually what it means, right? So we are having some kind of very large number here. So if there is nothing detected, it is going to have a default value of 999, or else if it is detected, it is going to have the raw distance. This front distance and right distance is what going to play a major role here. And the position, actually we are going to take both the position, the heading is an important thing here, because the orientation of the bot is what that's going to define our M line. So as you can see, if I go back here, if my bot is looking like this, let me say, if my bot is like this, I want to make sure the bot is first turning to this particular M line. So I want to turn this particular angle as my heading error. So I want to make sure this heading error should be 0 always. So that's what this orientation I am taking for the robot dummy handle. And then I am having the z-axis orientation, because the in x-y axis we don't want to turn. We want to turn in the z-axis towards the goal for the orientation. So I am getting the third index of orient robot, and I am taking similar way for the goal position and the dummy. So you all know that for distance calculation, what we will do? Square root of x square plus y square. For angle calculation, which is this particular theta I mentioned, what we'll do? Anybody? Simple kinematics. So if we are having a two kind of variables, one is y and another one is x, I want to know where y with respect to x, that particular angle. If I want to know that, what I'll do? Tan inverse of y by x, right? So that I'm going to do tan inverse of y by x here. This thing is pretty simple and similar to what we have did in our right wall following. And here I'm taking the tan inverse of this particular from the goal towards the, sorry, from the starting point towards the goal. So I am making this heading error is equal to angle to goal minus heading. So this heading is what actually the robot is facing. So I'll make here. Can I have a different color here? Yes. This is, let me say, this is the heading, and this is my actual orientation. So this heading and the actual angle to goal would be the heading error. So I am having this here, heading error. So where is it? This angle to goal minus heading would be the heading error. If the heading error is greater than pi, I want to, because we have to define everything in minus pi to plus pi, right? Because the angle may go minus 270 degree or plus 270, 180 like that. I want to define it within the range of less than 90 degree, minus pi to plus pi, sorry, 180 degree. So I am making that if it is the error is greater than pi, I want to make it lesser than pi by dividing it, sorry, subtracting it from 2 times pi. And if it is less than that, I have to make sure that it comes in range again by adding that. So this is pretty simple, but we are going to make the bot to move in that particular heading error. The distance to goal, if it is less than 0.5, we are going to have the simulation stopped and the goal is reached, and this is the general case. So we are going to have a backup recovery state. What is the backup? As we already did, if the front detected is greater than 0 and the distance is less than a particular defined value, which is 0.15 here, we are going to have the backing up state. I'll define that. The same avoid kind of case what we have did in obstacle avoid. The backup start time is equal to now. Now should have, I guess I forgot to define you in the earlier initialization. It should be in the initialization. The now should be having the simulation, current simulation time, and I am giving that current simulation time to the backup start time. We are going to do the same thing what we have did for obstacle avoidance. We are going to see whether the detected time minus the original time is greater than the duration, means we have to go back to our original state. So if the objective is very close, I am printing this message. If state is equal to backing up, what we are going to do, I am going to make the left joint to move in the opposite direction into this scaling factor. In a similar way, I am going to have the right joint to move in the negative same way to emergency reverse speed ratio. Both are negative, means it is going to move backwards. So I have different values for the emergency reverse speed ratio here, because we are going to have a pretty quick simulation there. And again, if now minus backup start time, now means the current simulation time minus the backup start time is greater than equal to the duration we have defined, yeah, now we are free, we are going back to the original state. Am I going fast or I am going in the correct speed? You all understood what I have said right now, right? Similar to the obstacle avoidance what we have did. Yeah, good. Yes, nice. So now, this is the main bug to state machine logic. We are going to define for both state move to goal, wall follow, and when we have to come back to the state move to goal. So when state move to goal, first thing what we have to do is to turn the bot in the direction of orientation. So for that, I have already calculated the heading error, which is the theta value, and I am going to make this as a scaling factor and turn according to that particular direction. So turn KP into heading error makes the bot to rotate in the orientation of the goal. So this turn is nothing but the maximum of negative base speed. This thing I think you can remember. What we have did to make them into the range of the maximum speeds, which is the base speed here. The same logic here. And now this came LV and RV, right velocity and left velocity, is now base speed minus turn and base speed plus turn. What does it mean? Base speed minus turn means the left wheel is going to move slowly and the right wheel is going to move fastly, which is nothing but the body is going to move in right side. But what if the turn is negative value? Already the turn is negative value, means base speed negative of negative will make it a positive and the left is going to have a higher velocity and the contrary will happen to right wheel. So we are going to move towards left. So when we are right or left motion, we are having the bot to move towards the orientation of our goal. So now we have achieved the orientation which is towards the goal, and now I guess we can have the move to goal condition. If front detected is greater than 0, if there is something, we have to go to the wall follow state. I'll give what wall follow state in the later time. This instance, no, when there is front detected is greater than 0, that is the hit point. So the current position of the robot should be stored in this hit point position, which is actually defined as 000 for the initialization purpose. And this at the instant of front detected is greater than 0, that distance we are going to take it as the initial distance. So now we are going to have the last recheck time is equal to this particular time. This is the last particular rechecked time. And I'm again going to follow the wall. The next recheck time will be later when I come back to the M line. Now I am going to the wall follow state. This wall follow state is kind of simple because the right velocity and left velocity should be made to the wall follow speed, because not the bot speed, base speed actually, it is changed to the wall follow speed as we have defined it earlier. The same thing, if there is an emergency condition seen, we have to have the backing turn, which I have already given emergency reverse speed, and here I am using emergency turn speed, not the reverse speed. Why? Because if I have both emergency reverse speed, it will come directly back. But if I have two different scaling factors here, I can have a back left or back right turn depending upon the value. I guess we can use this particular scaling factor here. So when the distance is less than this particular 0.25, we are going to have and if the right detected is greater than 0, what we are going to do is the same as what we have did in the right wall following bot. Calculate the distance error, maintain the distance between the bot, and we are going to have the value of left wheel and right wheel velocities. Rule 3, if there is no right wall detected, so there is nothing out there, we are going to check for the right wall by turning to right slowly in a fashion. So this is what we are studied in right wall following. So the major thing comes for the M-line re-entry condition. This is the very difficult thing, but I'll make easy to understand. So if now minus lost recheck time is greater than or equal to recheck interval, what I am saying is similar to the obstacle avoidance. If the recheck time and now I have set the recheck interval as 0.5 seconds, right? So if it is greater than 0.5 seconds, I have to recheck. Yeah, no, we have to recheck again like that. So if it is greater than that, I am making the last recheck time equal to now, and I am going to recheck for that. Recheck for whether the M line is reached or not. So I'll say how to recheck that. And if front is clear means the distance is greater than 0.6, so there is no obstacle there. And if we are closer to the goal, which is we are closer to the M line, I'll make it clear. There are three major conditions here. If these three conditions are okay, I'll turn on my video. There are three major conditions here. One, to make sure whether the bot is having no kind of interference between the goal from that particular point. One. Second thing, isn't there any kind of hit points or there anything? So I have to make sure whether the M line is closer to that. So I can go to the PPT. If I have come closer to the M line point like here or here, I have to make sure is it closer to that? Is it closer to the M line? And the third condition is whether the bot has crossed the M line. So these three conditions we have to check. If these three conditions are yes, we are going to turn back the wall to its original orientation. So yes, I can turn off. Yeah, now. First condition I have checked, front is clear, yeah, happy, nothing is there in the obstacle. Second thing, if I am closer to goal, I am checking this. If the distance to goal is less than that, the initial goal is at the hit point. If it is less than that, yes, I am closer to the goal, obviously. The third thing I am going to check is whether the robot has reached the M line or not. This is where the main thing lies. So now it is nothing but we are going to take a determinant of what X and Y positions. So I'll make it clear. So this is the goal X, goal Y, robot X and robot Y. I am going to have goal 1 minus hit point position 1, which is X directions, and goal 2 and hit point position 2, which is Y directions. This is going to be stored for goals. And for robot, I am going to do the same. Robot 1, robot 2 minus the hit points. So now I have all these four vectors, and I am going to have the cross product, which is goal X and receiver Y minus receiver X, so robot X minus into goal Y. So I'll make sure that this is in this particular orientation. I take the cross product of this, and I'm having some epsilon M line. Epsilon M line is nothing but some kind of predefined value to make sure it is some, you can have any values less than 0.35. 0.35 is actually, I'm like, the orientation is less than 35 degrees. Like that, I have made a pretty good, what I can say, manipulation. So if it is on the M line, I am going to know the cross product is less than the epsilon M line, which is less than 0.35. If it has crossed the M line, we are going to have a greater than. The angle tolerance I have had, as I said, I am going to have a rough 35 degree of motion. So now I guess the local facing goal, I am going to make the bot again to rotate in the initial heading orientation, which is the bot has followed the wall, right? I'll explain it in the simulation also. The bot has followed the wall, and hence I am going to make the, if the goal is not faced, I have to make sure that the goal is being faced. If all these conditions are met, which is the front is clear and the object is closer to goal than the hit point, and it is on the M line or crossed the M line, closer to the particular M line, and making sure the bot is in the heading orientation of the facing goal. If all these conditions are met, yes, the M line re-entry conditions are met, and we are going back to the move to goal state. I guess you are clear, because I didn't change the orientation here, because in move to goal state itself I have turned the orientation, right? So I don't want to redefine here. And then again, now it's a piece of cake for us. We are going to go towards the goal and we'll reach that. So this is some kind of debug messages I'm going to print, whether I'm going to get the front line is clear, or we are closer to goal, or on M line facing the goal. Like that I'm print, I guess. So I guess this cleanup is a simple thing. I guess you would be kind of in a clumsy state to know whether the bot is moving, what is happening. So I'll simulate it and I'll show you what exactly happens. So now I'll start this and pause. Now you can see the initial orientation was this, and I want to see here. So the bot is turned towards this direction, right? Well and good, we are facing the goal right now. This is the state move to goal, it is in the move to goal. Again I am resuming, it is going, and now we are going to see, yes, a hit point is reached. So we had a hit point here, and we are going to see there is no wall on the right side. So what we have to do, we have to turn right to check whether there is a wall. I am turning right, yes, a wall is detected. See, a wall is detected and the mode is changed to wall follow state. So now we are going to the orientation, we are following the bot similar to the right following. 1 second, okay, like this I'll have. So see, 1 second, yeah, now see, we are going closer to the M line, and the M line conditions is being printed here. No, the M line is not met, so we have to recheck again and again. Yeah, now we are going towards the goal. Yeah, yes, we are going following the right wall conditions here, and once the M line is reached, we are closer to M line, right? Front is obstructed, so we can't follow the M line because the front is not clear. When the front becomes clear, I'll pause the instant. Okay, 1 second. For an instant, the front will be clear. I guess something happened. I don't know why is it not moving. So I'll recheck and I'll say you why it is not going. It actually moved, right? It once the M line conditions are checked, it will move towards this goal, and we'll have the goal reached condition here. So I'll recheck this what happened here. uh, Sorry for the interruption. Hmm. So I want to know whether you had any kind of logical mistakes or logical misunderstandings here. So if you have any doubts, just say. Guys, are you having any kinds of doubts in the logic I have explained? I think we are having some kind of errors here. Errors in the sense in the logic. I'll clear it and I'll send you. It is not rechecking the M line condition. Wait for a minute. So guys, I guess you have understood up to now. I'm absolutely sorry, guys. Where is the starting? Yeah, here. So okay, I'll teach that in a different manner. Okay, now we'll go for the next demo, which is the vision sensor demo. For the vision sensor demo, I have a kind of moving these squares in the direction of orientation. So I'll say that. I'll show that once. Wait. This is kind of a funny thing. So there is no kind of big logics or kind of stuffs here. I want to make sure that these squares are going to move in this fashion, conveyor belt fashion, and we are going to have those recorded in here. So in the basic script, I have like just I am making the speed to increase with the simulation time. That's it. And if it is less than the minimum y, because we are going to less than negative values of y, I am going if less than minimum y, we are going to have it again from the start. If not understood, I will make this understand. So you can see they are moving, and if the minimum condition is met, it is starting from here again. And I hope you can see the difference between the vision of a perspective and an orthogonal vision sensor. This is just for a fun, guys. I guess this logic is pretty simple, and I guess you understood the major difference between perspective and the orthogonal type. So yeah, that's for today. Yeah, anybody having any kinds of doubts? And I'm really sorry because this particular thing, I don't know why it is not worked, and I have done for several iteration. It actually worked. I don't know why. I'll check. I'll check that out, and I surely update this working code to you. I'll just once recheck whether it is working. Um, Let it go. So, guys, did you had any kind of doubts in this session? One second, I'll stop presenting. If you have any kinds of doubt, just feel free to speak out.
Karthikeyan, actually, Danisha asked one doubt in the comment box. Please refer it.
Yes, yes. Why is it always right? Oh, yeah, you can do a left following bot. Yeah, that is what I thought of giving a task for you guys. You can do a left wall following bot if possible by using a left sensor, and the logic will be pretty simple, but just the contrary for that. Instead of increasing the left wheel velocity, you have to increase the right wheel velocity. That is the difference. You can do whatever wall, as there is only one possible condition I did. So now in the meet we have one of our former RCS representatives, Mr. Shakti Sundaramurthy Anna. Hi, na.
Hello. Hi, I got it.
Yeah, we can have a great applause to him because in his busy schedule for our workshop he has come. So now, have you seen the workshop? How is it going? Any kind of
Uh,
reviews?
I have seen the workshop from even the day zero. Also, I watched here and there. Like it's a pretty good workshop, and I must appreciate you guys that you took up this topic, which is a bit complicated, and did this much well. Even now, you are ready to explain them, right? The last thing you went
Yes.
wrong, right? So that is a
Yes.
thing which is very much required for the audiences also, and even for the people who participated in this workshop. I'm very much thankful to each and everyone, and it is a warm evening to each and everyone, I guess, because like the workshop to be success or like to be enjoyed is like only because of the participants, and it can be done because of the reciprocation and by the involvement of the participants only. It gives a push and to additional informations to be provided to you. That thoughts and all will be provided to us or the teammates only because of your involvement in this workshop and participating with the enjoyment. And I am thanking you from my bottom of my heart to each and everyone to spare your free time, your leisure time to spend in a productive and in a very enriching way with us. That is a great thing because many won't choose this thing or like to learn in a free time or they won't do so. But you did that, so I guess this would be because of the curiosity to learn new things. So I would wish each and everyone to keep this curiosity till your lifetime, which will keep and make you grow in a very large scale. And this curiosity is the basic thing, like a foundation for each and everything to learn new things and to uh, adapt new things and implement it and grow in greater things. So that is one thing which I felt. And to each and every people who taught and the team who organized it, I really would appreciate them. And guys, literally, can you all give a great applause to the teachers who taught this, like the people who taught you, because they also put their leisure time in order to spend to make you guys learn new things. So that is one thing which I wanted to say. And I guess we are also reviewing your feedbacks also. If anything is went wrong or you didn't get it, that is also we are reviewing and we'll surely get back to you at any time which is required. And apart from the certification and all, the thing which is important is your participation and your involvement, which you give, which you all gave to your 100%, I guess. And even the assignments which was given by the teammates, you all did with the enthusiasm, just not to be posted in the Instagram story. That is not the thing. The main thing is you have tried out of your curiosity. That is the thing. And kudos to you all for that too. Yes. So that is the thing which I wanted to convey, Karthik. Anything else?
Yeah, nah, like we have used this CoppeliaSim software for this workshop. Could you like
Yes.
say what are the future scope of this software after completing this workshop? Like what can they do? What are the future scopes? And
Mm, okay. Future scopes in sense like first thing would I would say that now they have learned the basics, right? So after this they might go for anything, like for sake they might attend any competitions also, or they might take up any projects in a large scale, or for DIY projects also. Anything, the base is like for everything, the design matters. Each and every, for sake, I'm saying in sake of robotics, in the field of robotics. So whichever project we take up or competitions which we go, there is a need to build any kind of robot or any prototype, anything. For that, the first thing would be required as a design, because we can't directly get into the hardware kind and assemble it and we check, because everything matters. Even for hardware, it costs so much, and each and every component it costs so much, and at last your time is being spent there. So if you spend all your time and money in those hardwares and you integrate it, and finally you find out that it is not reliable, or like for the condition which is given, it is not fulfilling. So in that cases and all, it will be a drawback for us, and everything would be wasted. So in that cases, first thing we might put a design, and we would implement it in the simulation software like CoppeliaSim. So this gives an upper hand for us in a such a way that we can build it and simulate it and test it, where we can test it with the real world environment simulation type, so which gives us a feel that and gives us the assurance which that it it fulfills the fulfills the requirements required in the real world environment or not. It is reliable or not, or what are the changes which we need to do. That and all will be helpful for us to uh, proceed with that in case of these simulation softwares. So that would be a base. And in further cases, if you are into learning many more things in education purposes, it is very much useful. And as I say, further you might even integrate with the AI and machine learning, because like I don't want to be very generic type AI or machine learning, because in this case we have done manually, like with the code. So in that case, in that code itself, we can integrate the machine learning algorithmic codes also, which might sense itself. I guess that was done. I guess I'm not sure. Well, Karthik, was that involved in that? Machine learning algorithm was involved, huh?
No, 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 no.
Okay.
It's not.
Okay, in that codes also can be integrated in this, and you can even test it also with yourself, like whether it itself is being following the code, and it is itself detecting the obstacles, like whatever the ML code which is being provided, is it giving a proper result or not, which can be done. And even for ROS 2, like robot operating system 2, the first thing we would design a robot, and we would simulate in this, like before implementing the ROS2 in the real world system, we would implement in the simulation software like CoppeliaSim. Because by 3 years back, I guess, we have conducted the same workshop along with the ROS2 also. So we in that we thought that how after completing the bot in the CoppeliaSim and simulation, how to implement the ROS2 also in that. So which gives an additional uh, hand to us in that robot. And even swarm robotics also it can be done in, like swarm robotics is basically a multiple fleet of robots in a simultaneous system, like everything would be independent, but in a it will be working in a coordinated way. So that is basically a swarm robotics, so that can also be tested here. So the scope is very high. The thing is like which we have to learn is like what, in which field or which scope are you interested. So that is one thing which I wanted to mention here. So with that, I guess that is enough, Karthik.
Yana, thanks for spending this much time for us to give a detailed thing of what and
I
why
guess
simulation
I
software
didn't
are.
bored any one of you. That is a thing, because like I want to give an informative thing. That's it. I don't want to bore anyone.
Thanks, thanks, Anna. Thanks, Anna.
Thanks, Na.
Okay, welcome. So apart from this, studies and all, leave it. Apart from this, anyone want to have any conversation?
Yeah, guys, it's very rare to see people like them who are busy, who are in their busy schedule,
Karthik,
spending time
please,
for us.
please.
So
I know he's over complimenting me. I'm not that worth it. I am that deserving. He's just too like too much. That's it. Karthik, please don't do it like this. Hey
guys, if
guys,
you have any, yeah,
yeah, continue.
if you have any kinds of doubts related to our today's session, for sure I'll change the code accordingly, because I can see that the front sensor is always detecting that's the major logical problem. I'll change the sensor or the range, and I'll send you the original .ttt file. You can verify that. Other than that, if you have any conceptual learning or any other kind of logical misunderstandings, yeah, you can, or outside of our context what you have spoke, if you have any other kind of general kind of questions to ask to Shaktiana or to us, you can ask. So it's our
Karthik, I
blessing to
guess
have
Rohit raised. I guess Rohit raised his
yeah, yeah,
hand for some technical doubt. I guess I don't know.
yeah, Rohit, see here, Rohit Ganabala.
I guess yes. He raised his hand. Okay, fine. I guess he have mistakenly pressed that.
Yeah, by mistakenly he made it, I think.
Fine, fine. No issues, no issues.
Yeah.
Okay, then, like, how many of you guys? Oh, okay, Tanisha, yes, yes. Okay.
Yes, Tanisha.
We're doing a technical issue, huh?
I think she's going to putting a comment, I think. I don't know.
Okay, let her know.
Yeah.
So, meanwhile, how many of you guys have enjoyed the 4 days of workshop? They might raise their
Yeah, if
hands
you
in
have any
the
kind of
comments.
general reviews.
Like, raise their hands. That would be fine. Because at last, the fulfillment of participants is much more important for us. Because this would help us, or would what to say, would encourage us to provide such more contents in future things also. Even this is just, I guess, this is a trailer, if I'm not wrong. In further upcoming days in the college also, once it reopens, my juniors and our teammates would provide you many more such improvised and better contents, I guess, in the form of workshop or less competition, anything. They have been planning, and it would be eventually let all you to know by Instagram posts and stories. So be tuned for that also. So that would be one thing.
Guys, 1 second, I have made that. The thing is like the sensors are placed in such a way like it is always friend detecting. So I have changed the ranges and orientation of this particular sensor for our condition of a cylindrical obstacle. So the thing is like, so if the right side wall is detected, we have to go in the right side, and the front should not be detected when it is over to the M line. So we have to make the front sensor to be like that. So now I have placed instead of a pyramidical type proximity sensor, I have placed a ray type. So now when all the conditions are met, we are again going back to the move to goal state, and now I can see the bot going towards the goal which is located there. So and the distance towards the goal is reducing, and once it reaches 0.15 we'll have the goal reached and the bug2 script completed. So it's actually the environment you will place, the logic remains always the same, and the environment you are going to place is what varies. So for my environment, I have to have a right sensor which is bigger so that I can have a right wall following without the hitting of the bot, because my bot robot base is very big, right? So that's an issue. So sorry for this particular inconvenience I have provided. So if you have any queries, you can ask always. I'll put this .ttt file to you. And for an information, I have a task for you. If possible, you can do. The task is like you can combine up this wall following concept either right or left and this bug to algorithm concept together, and you can have a maze solver bot, which is actually we can do very easily by an algorithm like A-star algorithms or much. And we have already had a workshop in offline for A-star algorithm, I guess. So, but for this concept, I want to know that you guys have learned this concept. That's why I want you to think of a logic to create a maze solver. But it's not mandatory to show your simulation. Just think of your logic and either do it or else you can make a simulation. So I will make sure if possible. I'll post it in the WhatsApp because someone have left. So that's why I'll post it in the WhatsApp. Or to Shakti if you want anything to say.
But pretty much I said what I want. If anyone is willing to convey, we can. Otherwise, we can definitely end the meet. If everyone is okay.
So, guys, can you hear me now?
Ah, yes, yes.
Yeah,
And
Danisha.
we are able to hear it. Yes.
Sorry, I guess it was a glitch there. So what was the scenario, right? Yesterday we had a workshop related to the model moving in a circular motion, right?
Yeah.
I actually tried it in my laptop today only. But what was the issue means my code was working completely fine. Even I checked with your team, Kishore and Jay. Both of them both helped me a lot. But my code is actually working great. But I don't know where I got the issue. My model is actually traveling in a straight line only, and it's not actually moving in a circular motion. So where could possibly the error be?
Yeah, that's being said. If possible, you can send your .ttt file to any of us here. We'll check with that, and
Yeah,
for sure within today
I actually sent that
file.
file to Jay. He actually worked the same code in his laptop and it works all right. But I don't know where I went wrong. I even checked with the model too and I checked with the code too. I don't know where it went wrong.
So the same file in another system is working perfectly, but in your
Yeah,
system it's not.
yeah.
So that can be, I think, what model did you use? Bullet 2.78.
Yes, Bullet 2.78. Actually
Mm.
tried with another model too. It's not working for the both.
But no error is showing at all.
No. Actually, code is working perfectly all right, but the model
Mm.
is not moving in a circular motion.
Okay,
Okay, then.
okay. Kindly check that mode. Which mode is there? It is in free mode or velocity mode.
Yeah, the join should be checked.
It was in
Just
free mode only. Actually, you called me right for the
yeah,
clarification. It was in the free mode only.
yeah. You
So
just
it should not be in the free mode.
yeah.
That's what I want to say. Like if
Okay,
I
okay.
have the left joint, it should be in the velocity mode. So you can see. That's what I said. I usually place a maximum torque in a higher value than 2.5 so that you can have a good torque of turning KP. So place it in velocity mode.
Okay, then
Maybe
I'll
that
try
could be
today.
a possible error. Yeah.
Okay,
If it is not coming, then also you can always contact us. We are here to help you.
sure. Thank you.
Yeah. Yeah, guys. Regarding the task, just give me the logic what you are going to implement for a maze solver. Yeah, Hariharan. What if the goal is inside a wall or surrounded by obstacles, and the only entry path to goal doesn't lie on the inlet? So what I'm saying is, whatever the obstacle is there, so if the goal is inside a wall, how you can achieve that, Hariharan? I can't say if the goal is inside the wall and the best possible way is not okay. I can understand. Maybe for that kind of conditions, we'll use a different algorithms like A star, or A star algorithm will work for any kind of logic purposes. But two algorithm fails in that kind of way, I guess. Or else this can be done by using three sensors where we are going to have a front, right, and left sensor. The it is going to follow. I'll explain once. Can I have a new slide? Yeah. Yes. Sorry. Hmm. Yeah, I had here, right. So you are saying like if a goal is here and there is a wall surrounded and the bot is here, so the M line is like this, and the only way to enter is not in the M line. Correct, Hariharan? Am I right? Yeah, I guess I am the right path. So if it is just like that the case, we have to implement three sensors, one in the front, one in the right, and one in the left. It has to follow the right wall all along the way here, and once this point is reached, it will start following the left wall along with it, and once the M line is reached, it is going to go towards the goal. Actually, the algorithm won't fail, but for our case, it is going to fail. So what I'm saying is, if the goal is case have a right wall here and right wall here, so we can achieve like this, I guess, Hariharan. Yeah, so we can have like but it's actually time consuming, as you can know. But bug to algorithm works in this kind of way. It will follow the right wall, and once the M line is reached, it will go back. I think your doubt have been cleared, Hariharan. If yes, put up thumbs up. Yeah, thank you. Any other doubts, guys? Just now, if there, you can end the YouTube stream. And if you guys are not having any kinds of doubts generally or according to the concept, you can leave the meet. And very, very sincere